Hello everybody. I want to give a brief tutorial on how we can use morphological erosion and dilation to get ways to subtract point sources or unidentified or unwanted background sources from images. And then thereafter, once we have something which looks like a clean image, or in quotes here, not having run through the clean program itself, but just cleaned the background sources, can be used then to obtain information about the characteristics of the source. Now, the first file we want to look at is something called a .csv file, which contains information about the sources we want to look at. I found that in general inside FITS files, frequency seems to be specified in various different ways, or maybe not, and sometimes the nominal frequency third axis is used for other things. So I've just decided it's sort of safest to specify the frequency at which we're observing in gigahertz on the first line. The following lines, which have a Python comment character in the front line, are basically just ignored by the following programs, but can be used to give us information about what's in the system. So here we have name of the source, nominal RA and dec, the position of the source in degrees and in declination in degrees. The largest angular size of 40 minutes in this case can be used if you want to say hunt for corresponding optical fields, and most information about a source requires you know its redshift, and we can specify a spectral index in the following column here, and if it's not specified, I assume that the spectral index of this source is 1. Now in our example here, we're just looking at one lonely little radio source, 3C236, and my following comment, blah, 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 means you can, if you have other sources observed at this frequency with this or FITS files of other sources observed at the same frequency, you can add in this information in these next lines, and then the program, the morphology program or the source fitting program will go through all these sources sequentially. Okay, that's that. Now we want to look at the following thing called example underscore script, which is also in the 3C236 run subdirectory. And here's some just sort of, initially there's just some sort of what I call bookkeeping, because I wanted to keep this original source around for just so we don't keep deleting it or whatever, and we link this thing to a source called 3C236.fits, and you'll remember from the CSV file that 3C236 is the name of the source we're looking at. Now, what we're going to do first is look at the initial flux density of this source, and this is, we run a program called get galaxy parameters, which reads the CSV file, and here we have some information about what we want it to do. First, capital F, or is obviously for false, says we do not want to dodge past the mask making part of this program. True means to use the noise as determined by a script adapted from Brazoro. False says use the original image and not a convolved image. And 6 says to get the parameters of all sources in the field which are greater than 6 times the noise as calculated by the Brazoro noise program. And you'll see that it reads in, if we had a whole bunch of extra sources inside this thing, it would go and process all those sources. And it's going to call this generate mask polygons program, which will pop up a thing on the screen which we can use for source selection, for subsource selection in the field. Then we do the same thing with get morphology images program, which I'll call a combination of morphological erode and dilate. And then it says we should use a disk source with a radius of 3. Again, the disks, we should be only detecting sources greater than 6 times the noise. We don't want to use dilation, and we want to we don't want to use the convolved image, but we want to use dilation. And in our case here, we're still going to find there's some leftover stuff in the 3C236 field, so we're going to do a rinse and repeat to get rid of remaining point sources in the southwest lobe. So then we're going to do the same thing, and we'll do an additional selection. Then in order to get a good integration of the remaining flux, we're going to convolve it by a factor of 2. And then we're going to get parameters again, but this time we're going to say don't skip the masking things, but instead of using the unconvolved source here, use the convolved source and get things which is all greater than 3 times the noise. So let's go ahead and try running this thing. So here's the first the first program to generate a mask. And what we can do here is, if we wanted to just zoom in and create a mask in this particular area, we can click on the Matplotlib zoom operator, and then we can click into this particular area. Now, in order to select objects for our actual flux density calculation, we have to use the left mouse button. Since the Matplotlib also uses the left mouse button to create zoom areas, you're going to see that there's a thing pointing to the corner of the initial image, and we get rid of anything we don't want by doing a right click. And in this case, 3C236 has 2 diffuse lobes here and here, and the central bright core source here. So those are the 3 which we want to look at or select. And then to select this program down to something which calculates image parameters, we then shut our window here using, in my version of Linux, this sort of circular close the window button. If you click on that, it's going to disappear, and then as we'll see later, I've done some output. We've now moved along to selecting objects for morphological erosion. Now, in the previous version, we wanted to select objects which we want to look at, but in this particular version, we want to select objects which we want to get rid of. And essentially, we've done 2 erosions followed by a dilation here, and you can see it's successfully picked up all these little point sources in the field. And let's say we want to get rid of most of the bright sources, because if we want to, say, do some simulations where we want to look at how, say, 3C236 would look at if you moved it to a redshift 2, but with the same telescope, then the size of the source and the signal is going to shrink. But since the beam of the original telescope is going to then increase relative to the apparent size of 3C236, we want to get rid of a lot of these background sources. So let's just amuse ourselves by getting rid of the strong background sources plus the bright central source. So we can click on the objects we want to remove. There's a little one right there at the end, and this little one right here. So let's, we then again, as before, we'll select these various polygons and we will delete them from the image, and then we're going to take that image and repeat this process. So here we are now with our process where we're going to repeat things. Let's look here first of all. Let's again get our image up to the source. Now, one thing that's quite well done here is that if we look at our central point source area, all that's left of the giant 5 Jansky source in the center of 3C236 is this maximum brightness peak here of about 2 millijanskys, 2.6 millijanskys or so. So 2.6 millijanskys divided by 5 Janskys gives us a residual of only 0.014%, which is actually a pretty amazing subtraction according to me. So let's go back out. And now we just want to go into the south little area here and get rid of this guy who's another background sources, but quasi buried in 3C236. So let's just go over here. Now we have to get rid of those lobe pointers which we don't want. So let's just click on this guy, or sorry, let's click on this guy. And so this one is now going to get subtracted off. And we do a subtraction, and then we do a convolution. So our next image here is going to be a convolution of this source. One can actually see, if you do a convolution, that there's actually some residual calibration instruments from this thing with a slightly more positive area in the north of the main source and a slightly less intense lobe down here. And I think that's just because 236 is long and narrow, and in the original Westerbork observations we would be getting most of the flux of this source at 1 hour angle, but in other hour angles the amount of flux being observed on short baselines will be lower. And I think the self-calibration at this epoch, which is about 1992, is much more of a focus on the point sources. So we got a fantastic subtraction of that, but there is some leftover stuff too in the north and south here. But that doesn't really affect our masking process, because we can just click on these two objects, and the source, the get galaxy parameters object will then take these two lobes and compute the source values. Now if we then look at the parameters file, let's just look at the original one. It's easiest. So this gives the name of our source. It gives us lots of information about the Brazorial median noise, and then we would tell it to, and since we're wanting to get flux greater than, I think, 6 in the original specification, we'll be looking for all areas which are greater than about 3.6 millijanskis, and then it produces various equipartition, etc. parameters based on our, since we didn't give any specific spectral index, it just uses a default one of 0.75 for the entire source. But then using the Shapley polygons analysis program, we can actually look at the individual parameters of the lobes, which are here, the two lobes which are here and here. And it figures out that the point source in the middle is actually a point source with an integrated flux of about 5,400 millijanskis, and the peak flux density itself is somewhat less than that. But it's if you examine that 3C236 source closely, you'll see that the central point source is not sitting precisely on a grid point, and so the integrated flux covering the actual beam area is probably going to be slightly bigger, as it is in this case. So and that way you can determine if, for example, if the some of these sort of equipartition parameters of the total source, blah blah blah, etc., agree reasonably well with that of the individual lobes. And because of this enormously strong central source, a sort of dumb equipartition calculation gives, for instance, larger magnetic fields, etc., than is the case in the individual lobes. So the individual sort of lobes give a better estimation of the basic internal source parameters. So that's basically what I wanted to say, and hopefully you'll find this system enjoyable to use.